All right, everyone, we're just going to introduce one small new topic and then do a little bit of review today. You're going to have some review questions. Just make sure, as you do the math stuff, you're actually doing it, not relying on just my answers. So the first thing we're going to talk about is just kind of a new term. The term is ohmic. So any object that obeys Ohm's law, so just to review what Ohm's law is, R equals V over I. But remember, we can write it another way, V equals IR, or we can rearrange it again, I equals V over R. I prefer the last way. That's generally the way I am going to write it, but any of those are fine. You can work on your algebra to figure out how you can rearrange those in that way. So any object that obeys Ohm's law is said to be ohmic. Ohmic. Okay, that means they have a linear relationship between voltage and current. Okay, because, well, we'll look at the graph in a second. Any object that does not obey Ohm's law is said to be non-ohmic. Okay. In this class, we really only deal with ohmic objects, So, ohmic objects have a linear relationship. Non-ohmic objects do not have a linear relationship, okay, between voltage and current. Because if you recall, just to remind you, let's write V equals I times R. If this is on the y-axis, if V is on the y-axis, and I is on the x-axis, then that means that R has to be the slope. Okay? So it says explain why the solid line represents Ohm's law, or an ohmic object, and the dotted line represents a non-ohmic object. Well, this represents an ohmic object because it is linear. It's a linear relationship between voltage and current. And this one here is non-ohmic because it's not a linear relationship between voltage and current. Okay, so if there's a linear relationship between voltage and current, it's ohmic. It follows Ohm's law. If it's not linear, it does not follow Ohm's law. It is non-ohmic. All right? That's all you really have to know. You have to be able to identify, oh, that's not ohmic. And the reason being, it's a curved line. Oh, that is ohmic because it's a straight line. Again, on a voltage versus current graph, or a current versus voltage graph. All right, so let's get into some questions here. So I would recommend you guys do these questions on your own first, and then look back in a second for the answers. All right, I'm going to go through these pretty quick, so I'm just going to write all the givens down first. So for this first one, V equals 12 volts, and the resistance is 30 ohms. I'm going to start with the way they write it on the equation sheet. R equals V over I. R is 30 ohms. V is 12 volts over I. So we effectively get 12 divided by 30. And that's 0.4 amps. All right. On to the next one. So we have I equals 2.3 amps. And we have R is 5 ohms. I don't know what I just drew there. 5 ohms. We're looking for V. So R equals V over I. 5, I'll leave the units out for now. V over 2.3. You end up cross multiplying here, and I think this one comes out to be 11.5. It is. Oops. Excuse me. 11.5 volts. All right. We have 6 volts, and we have a current of 1.6 amps. R is our unknown, the resistance. Works out nice this time. R equals V over I. V is 6 volts over 1.6 amps. 6 divided by 1.6. I just did 6 divided by 16 accidentally. So again, 6 divided by 1.6 is going to be 3.75. And we learned last class that we use conventional current flow, which is the flow of positive charges. So for example, let's say you have a wire and all the electrons are flowing this way. Conventional current flow flows the other way. All right? Just the way we do it. All right? Not a big deal. All right. This one says list 3 ways. So I gave you this little chart here to remind you of how things affect resistance. So just give yourself a second to read that. All right, so list 3 ways to reduce the resistance of a copper wire. So take a second to do that. You can make it shorter. You can make it, now do we want to be wider or narrower to reduce the resistance? We want to make it wider, right? Think about like the hallway. Easier to get through a hallway if it's really wide, less resistance. And think about how temperature affects it. So to reduce resistance, we want to make it colder. We might talk about it a little bit later, but if you ever heard of things like superconductors of electricity, they make them really, really, really cold so that electrons can move through the material really, really easily. So for 11 and 12, look at the picture to the right. You have a battery. This represents a battery, this little symbol here. We'll get into circuit diagrams later. All right, so as the temperature of the nichrome in the circuits decreases, okay, so as the temperature goes down, what happens to the resistance? We just said, as you make something colder, what happens to the resistance? Okay, if you make something colder, colder equals less resistance. Okay, therefore, the bulb will become brighter, dimmer, remain the same. Well, if there's less resistance, what's happening to the current? Okay, let's write our equation like this for now. If you want to think about it mathematically, I equals V over R. If R goes down, there's an inverse relationship between R and I. What has to happen to I if R goes down? The denominator gets tiny. I has to go up, right? So it's going to get brighter. Okay. Go back to the simulation from last class, make a light bulb, make the resistance in the light bulb go down. Look at what happens when you do that, all right? 13 is probably one of the harder questions. It's a bit of a math question. You have 2 wires, wire A and wire B. Let's see, both wires are made of silver, great. Both wires have the same temperature, great. Wire B is twice as long, but wire B also has twice the cross-sectional area. So how does the resistance of wire B compare to wire A? So here's what we're going to do. We're going to write down our resistance equation. R equals rho L over A. Okay. So here's what we're going to do. This is going to look a little familiar. Let's take wire B for a moment. Now, we've done this before. If I replace something, or if I change it, if I don't change it, I replace it with a 1. If I change it, I replace it with the factor I'm changing it by. That should be really familiar to you with the force of gravity and the electrostatic force. So for example, compared to wire A, does wire B have a different rho value? No, they're both made of silver, so put a 1 there. Does wire B have a different L value? Yes. How much bigger? Twice as big. So you put in a 2 there. And then the cross-sectional area. Does wire B have a different cross-sectional area? Yeah, it does. How much bigger? By how many times? 2. So this ends up being 1. So wire B has 1 times the resistance of wire A. That sounds a little weird. You know why? Because wire B has the exact same resistance as wire A. Excuse me. Okay. Yes, wire B is longer, so it has more resistance. But wire B has twice the cross-sectional area, which leads to less resistance. Those two, the increase and the decrease, cancel each other out. Therefore, wire B has the exact same resistance as wire A. It's a tough question. Go over it again. Try to do it from scratch. Try to make sense of it to yourself. And then move on to the next one. A lot of words here for 14 and 15, but they refer to this picture right here. Let's see. A circuit. Let's see. There's 12 volts in the circuit. So I'm just going to write down the givens now. I don't know if I need it. Okay. Variable. Okay. Nichrome wire. I might have to look up what that is later. The length of nichrome wire. Actually, no, let's look that up now. Nichrome was a class 117 maybe. Yeah, nichrome. 150 times 10 to the negative 8. Ohms times meters. All right. The length of the wire can be varied and whatever. The Oh, the length of the wire. Let's write that down. Length of the wire is 10 centimeters. So L is 0.1 meters. And the ammeters read current, remember? So the ammeter current is 2 amps. All right. So what is the resistance of the wire when it's set to 10 centimeters? So we have a lot of info already. R equals V over I. 12 volts over 2 amps. And we have 6 ohms. Okay, what is the cross-sectional area of the wire? So for this one, we have to type in our equation rho. R equals rho L over A. Our R value was our answer to the last question. I think that one's going to be 6 ohms. So I'm going to leave the units out. Rho is 150 times 10 to the negative 8. L is 0.1 or 10 centimeters. And A is our unknown. All right, so basically what you're going to cross multiply. And we have 150 times 10 to the negative 8 times 0.1 divided by 6. We get A equals 2.5 times 10 to the negative 8 meters squared. And the last question here, which would cause the greatest increase in the rate of flow through a conductive wire? So remember, rate of flow is current, right? So greatest increase of current. All right, so think about what's going to increase the current. So remember, our current equation is I equals V over R, okay? Right, R equals V over I, rearrange it, I equals V over R. So potential difference, that's voltage, or V. So would increasing or decreasing V make I bigger? V's in the numerator. So would you want a big V for a big I, or you want a little v for a big I? Hopefully you realize you want a big V, right? There's a direct relationship there, or a linear relationship. So you can eliminate choices C and D. Those say that you would have to decrease the potential energy. Now think about the resistance. What do you want with resistance here? You want very little resistance. What would give you the least resistance? The least resistance, would that be a short wire or a long wire? Okay, because as R goes down, I goes up. So which would give you the least resistance, a short wire or a long wire? Hopefully you know it's a short wire. All right, so make sure you check out the exit ticket. Make sure you fill it out before 8 p.m. And if you have any questions,